Okay, so I thought it would be good to see some more example of solving recurrences using the recursion tree methods, because that's my favorite method. So let's start with the following recurrence. T of n is equal to 2tn over 2. So this seems very similar to recurrences we already see, but now n over log n. Okay, and the nice thing about this recurrence is that the solution is kind of surprising. So first, the recurrence looks very, ignore what's written here. Think about the black box. This is very similar to the recurrence for merge sort. So we know how the recurrence tree looks like. It's a binary tree. It's going to have logarithmic depth, right? In the ith level, we are going to have 2 to the I nodes, right? And the size of the subproblem in them is going to be n over 2 to the I, right? Now, if we look on the recurrence here, the value that we have to pay is n over log n. Let's assume the log is on base 2 just to make things easy. So this is going to be, for every node here, for every one of the nodes here, the value that is associated, the amount of work spent in this node, ignoring the recursive call, is going to be n over 2 to the I divided by log n over 2 to the I, which is n over 2 to the I, right? Log n minus I, right? Because to remind you, log of A, I used here the fact that log A over B is just log A minus log B, right? That's what I used here. And the second thing I used is that log of 2 to the I is just I, right? Okay, so we get this. Okay, so let's summarize. For every level, we have 2 to the I nodes. Every such node give a contribution of what I just wrote there, n over 2 to the I times 1 over log n minus I. Right? This is the contribution, the total amount of work involving all the nodes in the same level. 2 to the I cancels out, so this is just n divided by log n minus I, right? Now we have to summarize this on all the level of the tree. They're of log n levels, right? So let's write down the summation. This is the contribution per level. This is equal to this. Now we have to summarize this, right? But we can just change the limit of the summation to go from 1 to j, going from 1 to log n of 1 over j, right? I just reversed, I summed this is just reversing the summation. The elements are being summed the same, but in reverse order. And this is just the harmonic sum. And the harmonic sum is just the sum of the first log n is h of log n. And you can think about h of n as essentially being log n. It's theta of log n, right? So as such, we get that the solution to the recurrence is n over log n, which is pretty surprising, right? Because somehow you would think that, my first guess for the solution of this recurrence would have been linear. So, so you have to be careful because sometimes intuition lies. Okay, here's another example. 2 to the n is equal to t of square root n plus 1. So, so this recurrence tree is not really a tree. It's more of a list, right? Because there's only one recursive tree, right? N, square root n, square root n, right? Square root n. And of course, the question is, how do we know how deep we have to go before this becomes 1, right? What is the height of this list, right? So the trick to observe is that log of square root n, this is just log of n to the power half, and log, to remind you, log of a to the power b is b times log of a, right? So log of square root n as such is going to be equal to half of log n, okay? So really, if you write down the number of bits in each number instead of n, then this is log n, this is log n divided by 2, next level is log n divided by 4, oops, and so on. So in particular, if you go, we have to, the ith level is going to be log n divided by 2 to the I, and we have to continue until this becomes smaller than 1. So clearly, I has to be log n, right? So the depth of this recurrence is log n, because of the argument I just did. And now the summation is just in this tree, the tree of depth log n. Every node has value 1, so the total amount of work is log n. So this is the solution to this recurrence. And this recurrence is really recurrence about the depth of the tree. And in particular, here is a cute example of using it. This is the this recurrence, which is very similar to the previous one, except that instead of doing one recursive call, we do square root n recursive call, and instead of n, this is previously it was 1 and now it's n. Right? So now we have to draw the full-fledged recurrence tree, okay? And the root has square root n children, and every node in the next level has n to the 4 children, and so on. And the important thing to observe is that first, the depth of the recurrence is going to be h of n is equal h of square root n plus 1, right? And this is exactly what we already solved, so this is just log n, right? So this recursion tree has depth log n. The second important thing to observe is that the total size of the sub-problems or the nodes in every level of this recursion tree is going to be linear, right? So as such, every level is going to, and the contribution of every node is linear in its value. So the contribution of every level in the tree is linear. There are log n level, so the total summation is n log n. Okay, next example. Okay, what happened if we run Quicksort, but somehow we always get somewhat unlucky, loop-sided, right? They always call recursive with a subproblem size n over 4 and 3n over 4, right? So this is looks a bit bad, and the question is, what is the solution to this recurrence? So first, the observation is that we can write again a recurrence for the depth of the recurrence, depth for the recursion tree. So h of n is going to be h smaller equal than h of 3/4 of n plus 1. And if you think about it a bit, the solution to that is O of log n, right? Because the way to think about it is that if you go 3 levels down in the recurrence, you get 3/4 to the 3, which is whatever, it's 27 divided by 64, which is smaller than half, right? So after going 3 levels down, the problem size is smaller by half. So after log n level, you're done. So the depth of this recurrence is log n of this recurrence tree. And now, so the depth is log n. Now we are in a bit of a strange situation because nodes in the same level have different sizes, right? But it doesn't matter because we pay linear term in each, the amount of work in each one of them is proportional to their size, so it's linear in each size. And the important thing is that in every level, the total size is exactly n. This is where we are using very critically the fact that n over 4 and 3n over 4 is just n, right? So this is linear in every level. We have log n level, and this is the solution to this recurrence is n log n. Okay. Okay. And I believe that this is it. So I hope this example will be useful for you when you encounter recurrences.